Hi, we are from Group 12, TMF2234 operating system. Our group consists of 5 people. AMISHA RITTNER, AMIRA NAJWA, HANISAH IBRAHIM, HANISAH ZAIN and UMMIE NAJWA. So I'll be talking about introduction of round robin scheduling. Round robin scheduling is a primitive scheduling algorithm. In round-robin scheduling, all processes are executed in cyclic manner. Each process receives a fixed time slot, known as time quantum, during which it can access the CPU's resources for execution. Once a process has used its allocation time quantum, it will switch to the next process in the queue. This cycle continues until all processes are complete. By employing this method, we can minimize wait times and ensure a responsive system that keeps applications running smoothly without allowing a single process to monopolize the CPU resources.
Thank you, Hanisah. Hello, my name is UMMIE NAJWA and now I'm going to execute the C program. As you can see here, this is the main menu of our program. Here, we can enter the number of round-robin loop. As mentioned in the project question, there are 12 different time quantum that we need to test in the program. So here you can put any number from 1 to 12 depending on how many times you want the program to loop. I will just put 2. As required, we need to evaluate the job list using different time quantum. Let's say we evaluate using time quantum 30. After we enter the quantum time, a list of performance metric for the job list appear in the table form. The performance metric that we have here is turnaround time, waiting time, and number of interrupts. Below the table, as you can see, we have the calculation for average waiting time, average turnaround time, and average number of interruptions. This calculation will provide us the data that we need for analysis and evaluation of round-robin algorithm later. Since I have input 2 times for the program to loop, then I can still evaluate for the next time quantum. I will evaluate for the time quantum 45. So this is the performance metric for time quantum 45. That's all from me. Thank you.
Hello, my name is HANISAH with the matrix number 85103. We'll be explaining how we get the calculation results. So, firstly, this part of the code gives us the total waiting time, total turnaround time, and total number of interrupts. Waiting underscore time represents the total time a job spends waiting in the ready queue before it begins execution. Finish time is the completion time of the current job. Job B.arrival time is the arrival time of the current job. Job B burst pre-E is the preemptive burst time of the current job, which is the time the job spends in the CPU during each time quantum. The formula calculates the waiting time by subtracting the arrival time and preemptive burst time from the completion time and adding this to the current total waiting time. Finish time minus job B arrival time calculates the time elapsed from the arrival of the job to its completion. If the value is positive, it means the job has spent some time waiting in the ready queue before it started execution. So, when we subtract job B.arrival time from finish time, we are essentially subtracting the time the job spent waiting in the ready queue from the total time it took to complete. This provides an accurate measure of the waiting time for the job. Turnaround underscore time measures the total time taken for a job to complete its execution from arrival to completion. Finish time and job B arrival time are the same as before. The formula calculates the turnaround time by subtracting the arrival time for the completion time and adding this to the current total turnaround time. Finish time minus job B arrival time gives us the total time for the job spent in the system, from its arrival to its completion. If this value is positive, it means the job had to wait in the ready queue before it started execution. If it's negative, it means the job completed before its expected arrival time. which might happen in certain scheduling scenarios. Turnaround time then added to the current total turnaround time. The variable turnaround time accumulates the turnaround times for all processed jobs. Num interrupts calculates the number of interrupts by dividing the preemptive burst time by the time quantum and adding this to the current total number of interrupts. In preemptive scheduling, such as round robin, jobs are interrupted and put back into the ready queue after a certain time quantum. Job B.burst pre is the same as before. Qt is the time quantum. So, job B burst pre divides by Qt calculates how many complete time quanta the job's preemptive burst time can be divided into. This gives the number of times the job would ideally like to run without being interrupted. Num interrupt then added to the current total number of interrupts. The variable num interrupt accumulates the total number of interrupts for all processed jobs. This part of the code calculates the average of waiting time, turnaround time, and number of interrupts. The division by 30 is part of the output formatting for the average values. Here, waiting underscore time, turnaround underscore time, and num interrupt represents the total waiting time, total turnaround time, and total number of interrupts, respectively, for all 30 jobs. The division by 30 is done to calculate the average values per job. It is also for normalization to get average values per job in the output.
Hi, I will talk about the calculation result in the output program. I use the diagram which the user had entered the value of time quantum which is 5 and the round robin in one loop. As we can see here, the output had listed all 30 job lists that had been given in the Excel and interpret here. All the performance metrics such as arrival time, burst time, completion time, turnaround time, waiting time, and last but not least, number of interrupts has been calculated during the program runs. Arrival time refers to the instance when a process enters the ready queue. Burst time is the total time required by a process to complete its execution from the moment it starts running until it finishes. Completion time signifies when a process completes its execution and exits the CPU. Turnaround time represents the total time taken by a process from arrival time to completion time, including both waiting time and execution time. Waiting time is the cumulative time a process spends in the ready queue before getting CPU time. The number of interrupts indicates the frequency of interruptions or context switches during the program's execution, highlighting the responsiveness and multitasking capability of the system. These metrics collectively provide insight into the overall performance, efficiency, and responsiveness of a scheduling algorithm and help in optimizing system resources and improving user experience. So we can see here at the bottom of the result, all the average of these performance metrics had been calculated by dividing total number of each performance matrix with 30 job lists.
From this table, it shows the comparison of different time quantum performance. Here we compare different time quantum. In this project, we are given time quantum 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and 60. I'm not going to read out all of the result of the average, but here I would like to conclude that as the time quantum increase, the average turnaround time, the average waiting time, and the average number of interrupt decrease.
For the best time recommendation, we have used charts to compare the data of the average time quantum performance, average turnaround time, average of waiting time, and total number of interrupts with different quantum time. When we compare the full data, we can see that the time quantum 40 has the lowest average turnaround time and lowest average waiting time. For the total number of interrupts, the time quantum 40 is not the lowest value, but it is considered low number integrate. Therefore, we choose 40 as the most appropriate time quantum for our job list. This is because it has the lowest average turnaround time and average waiting time. It also has a lower total number of interrupts. The performance of round-robin scheduling is highly dependent on the time quantum. When the time quantum is too small, the overhead will occur, resulting in a significant number of interrupts. So, when the time quantum is high, the scheduler will become the first conclusive algorithm. In conclusion, based on the result, it is recommended to use time quantum authority. However, the results might change when the program evaluates different job lists and results in change of recommendation for time quantum. In short, the program only evaluates the performance of round-robin scheduling algorithm and provide data, but does not provide the best time quantum. That's all from us. Thank you.